Hello everyone, and welcome to this video titled Derivatives of Exponential and Logarithmic Functions. In this video, I'm going to be taking you through a preview version of a Knewton Alta assignment, also titled Derivatives of Exponential and Logarithmic Functions. Please understand that this is a preview version, so the questions I work on in this video may not be the exact same questions that you see when you work on the assignment yourself. But the objectives are all the same, and the methods I use should be similar to the ones you're using to solve these problems. All right, so here we are at Knewton Alta, preview of derivatives of exponential and logarithmic functions in the particular course I'm teaching, that is section 3.9. In the upper right-hand corner, you should see a mastery bar that shows you how far along you've gotten in the assignment. Next to that, an activity log, which shows you all of the objectives in the assignment. So this particular assignment looks like has 8 objectives broken up into 3 headings. So you have derivatives of exponential and logarithmic functions of any base with base e, and then a method of differentiation called logarithmic differentiation in the last heading. Now I have the settings in this assignment set up so that if you would like to move to a different heading at any time, you can go to the activity log and hit start. So right now I'm starting off in this derivatives of exponential and logarithmic functions with base e area. So they'll be cycling me through these 3 objectives first before moving me to another area, unless I wish to start it early. But I will not be doing that in this video. All right, then you have your current objective, a question related to that current objective, and at the bottom of every question, you should see a feedback button. So this, if you see any issues with the question itself or the answer explanations after the question, you can click on this and send feedback directly to Knewton support, and hopefully someone will get back with you, relatively quickly and address your issues. The instructor cheat button will not be there for you. Right? This is for instructors only to fill in answers while, doing demonstrations. So I will not be using that in this video. And then you have the more instruction button. So if you're ever working on a problem in a particular objective and you don't recall how to do that particular question, or you don't remember the material too well from your reading and studying, click on more instruction, open instruction, and you'll be given reading to do or videos to watch or both that relate to that objective, and hopefully that can help you get through the assignment. All right. So before I go into these questions, I want to talk about, the title of the assignment, derivatives of exponential and logarithmic functions. And I'm just going to get all the rules out right away, and then we'll start using them. So I like to start with derivatives of logarithmic functions myself. specifically log base e. Remember the natural logarithm? So say we're given, f of x equals the natural logarithm of x. And just to refresh you as to what that looks like, remember your log functions with a base larger than 1. Here I am at the desmos.com. It's a free online graphing calculator site. So remember, here was the natural log or log base e of x, right? You had 1, 0. Base was larger than 1, so you had the graph, the function was increasing as you went from left to right, and only for positive values of x, right? The y-axis here would be a vertical asymptote. The graph's going to, the output's going to negative infinity on the right side of the y-axis as x approaches 0 from the right. All right, so there's our curve, right? The natural log function. So now I'm trying to find the derivative of such a thing. So I'm going to go through and use our limit definitions, right? One of them anyway. So remember, one of our limit definitions of the derivative was, the f prime, the slope of a tangent line, right, would be the limit as h approached 0 of, and then we had, slopes of secant lines in here, where at one point we evaluate at some x, and then at the other we evaluate at x plus h, and then do the little rise over run. So the value of this function at x plus h, so natural log of x plus h, minus the value of this function at x, and then divided by the run, which would be x plus h minus x, or just h. And then if you, let h be 0 here, the numerator and denominator would both be equal to 0. You'd have this numerator approaching 0, denominator approaching 0, limit, right? 0 divided by 0 was one of those indeterminate forms, right? Meaningless, nonsense. So I have to retool this, right? And I'm going to retool it in such a way that our derivative will have meaning. We'll actually be able to get an expression out of this using properties of logarithms. So this is the limit as h approaches 0. Now this all over h here, dividing by h, this is the same thing as times 1 over h. So I'll put that out front. And then remember, when you subtract two logarithms with the same base, you can make a single log out of them. So a single natural log where it's the first argument divided by the second one to make the new argument, it's the quotient property, log of a quotient. So then we have x plus h divided by x inside this log here. And then I'm going to still retool this, dividing each of these terms, the x plus h by x, and also using the power property. Remember, when you have a coefficient of a logarithm, you can put that number inside as the power inside. So we have the limit as h approaches 0 of now the natural logarithm of, and when you divide x plus h, each of those by x, that would be 1 plus h over x for the base, and then this 1 over h going inside as the power, so raised to the 1 over h power. All right, and what I'm going to do with this, so you see this is 1 plus h over x. I like to raise to the reciprocal of h over x for reasons I'll discuss in a second. So this power up here, this 1 over h, I'm going to multiply this by x over x. That way I'll get the reciprocal of h over x. I'll get x over h, then times, 1 over x. So we have the limit as h approaches 0 of the natural logarithm of 1 plus h over x raised to the x over h times 1 over x power But now up here, this product, this x over h times 1 over x, and when you have a product in a power, you can retool that, rework it, write it as an expression where you have a power raised to another power. So one more time here, we got limit as h approaches 0 of the natural log of 1 plus h over x raised to the x over h, and then this again raised to the 1 over x. Lots of parentheses here. So there. 4 right ones, 4 left ones. Okay. Now this expression inside the logarithm, all right, this 1 plus h over x raised to the x over h, and then again that's raised to the 1 over x. You may recall from maybe a pre-calculus course or some college algebra course before this, that when you have an expression like this, 1 plus, something, so a little unknown box there, raised to the reciprocal of that thing, right? So 1 over that thing, flip that thing over. So this is like the 1 plus h over x raised to the x over h. This approaches that value e as the value of the expression in the box here approaches 0. And that would be happening here, right? Because x is a fixed number in this, right? X is fixed. What's changing is h. So if x is a fixed number and h gets closer and closer to 0, h divided by x would get closer to 0 divided by x. And again, x is some positive number here, right? We're talking about log of x, so x got to be a positive. So this h over x, the expression in the box, is approaching 0, and I have 1 plus that expression raised to the reciprocal of that expression. So this thing I have in the orange box here, when I take the limit as h goes to 0, this is going to e. So we end up with, after taking the limit, the natural log of e to the 1 over x power. And then you might recall also that these logarithmic functions and exponential functions, right? This is an exponential with base e, a log with base e. Those are inverses. They undo each other when you compose them like this. So I'm left with just 1 over x. I'll bubble this in. This is the important part of all this, right? So I'll write this on the next page on its own. So if you're given the natural log of x, just plain old x, then the derivative, right, f prime, at any point, the slope of the tangent line at any point of that natural log curve is just the reciprocal of the input, 1 over x. All right, so there's the derivative of your logarithm base e. So now say we're given a logarithm with some other base. So f of x equals, say, the logarithm log. I'll just do base b here for, any base of x. So again, b was a positive number as well, right? You only worked with positive bases. Well, instead of having log base b, we can rewrite this so it involves natural log base e. So again, I'm not going to go into all this, but you hopefully recall some properties of logarithms and how you can rewrite a log with one base in terms of another base, right? The change of base rule. So instead of log base b of x, I can rewrite this as the natural log of x. But then don't forget to then divide by the natural log of the original base, right? So natural log of x divided by natural log of b. So now when I do the derivative, this natural log of b is a constant. So I have a coefficient, all right? This is 1 over the natural log of b. Remember, coefficients, constant multiples stick around, multiplied by the derivative of the natural log of x, which we just saw was 1 over x. Okay, and then multiplying the numerators, multiplying the denominators here, we get the following. So if you're given a logarithm of, any base, not just base e, say base b, its derivative is 1 over, the expression inside the value of x, but then there's also this factor of natural log of the original base down here in the denominator times the natural log of b. Okay, so I'll bubble that in. That's the derivative of your general logarithm of any base. And of course, if the base were e, then this natural log of, e down here would just be 1, and your derivative would be 1 over 1x, which we saw earlier for log base e. Okay, so we've seen now a rule for the derivative of any logarithmic function, right? Logs with any base. And now we go to our exponentials, and we're going to use the logarithmic derivatives to help us find the derivatives of exponential functions. So again, suppose we're given f of x equals, or y equals, I'm going to call it y this time, e to the x power. All right, y equals e to the x, same thing. So again, real quick reminder as to what that looks like, an exponential base e. So there's this y equals e raised to the x power. And remember, this is just the inverse of the natural log function. Here's the graph of y equals x. Make that like a dotted line. So you see how the red graph and blue graph are just reflected across this green dotted line, right? These graphs are a reflection across the line y equals x. You just switch x and y on one graph and you get the other graph. They're inverses, right? Remember, logs and exponentials with the same base are inverses. So I'm going to make use of that fact. So remember, if y is e to the x, this means the same thing as the following. It means that x, right, the power on e there, is the logarithm base e of y. Now again, nobody really writes this. You're not going to see this too often. So x is the natural log of y. And I'll show you. Right, we'll go back to Desmos here. I'm going to enter this equation, and you'll see it's the same graph. It's going to have the same exact points, the same ordered pairs, x and y values satisfied. So again, here's your e to the x curve, right, this blue curve here. And if y is e to the x, that means x is the natural log of y. And you see it comes right on top. It's the same exact curve, same exact points. So from here, I'm going to now find y prime using implicit differentiation. Or we could go through and do that inverse rule we've seen in the past, but I'm just going to do implicit differentiation, right? So I'm differentiating both sides, with respect to x, the independent variable x. On the left side, the derivative of x is just 1. And on the right side, right, you got the natural log of some function of x, right? Again, it's not just natural log of x, it's the natural log of y, and y is implied to be a function of x, so it's the natural log of something. So I got to do chain rule here, right, when I go and differentiate this. So remember from earlier, the derivative of the natural log of something is 1 over that thing, or the reciprocal of that thing inside. Then afterwards, right, chain rule being applied here, times the derivative, right, of that thing inside, the thing prime. So same thing here on the right side, you got, derivative of the natural log of y would be 1 over y. Then afterwards, chain rule applied times y prime. And then if you were to solve for y prime, all I would have to do to get y prime alone here is multiply by y, and 1 times y is y. And look, y prime is exactly the same as y, which was, initially this e to the x. So this is a function whose derivative is equal to itself. All right, so that's huge, right? That is very nice. So the derivative of e to, exponential with base e is itself. And then you might have chain rule going on, if you have an expression put into the power, a function composition going on, you might have to use a chain rule after. But if it's just plain old e to the x, its derivative is itself, e to the x again. And I'll show you about the whole chain rule thing. So what if I had a different base? All right, so we know this now. The derivative of e to something, is itself. So now let's look at other bases. All right, so here's an exponential function, say f of x or y equals, and then some base, right, b to the x power, right, where again the base has to be positive to be, useful. So you could also call this y equals b to the x. Well, you could if you wished. If you wanted to get this to be written in terms of base e, just use the fact that e and the natural log are inverses. All right, you take any number. For any number n, you can call it, e raised to the natural log of that number. And of course, it probably should be a positive number. I mean, this works for negative numbers too. Just the logarithm of a negative number uh, would be imaginary, have an imaginary part to it. And zero, natural log of zero is undefined. So like, I'm gonna say for n positive, right? And this should be positive, right? You take any positive base, raise it to any real number power. This is a positive quantity, this b to the x is greater than 0. So I can rewrite it as e to the natural log of itself, right? The natural log would be the e and natural log would undo each other here, and I'd be left with b to the x. And then I use the property of logarithms, where if, that power property, if there's an expression inside a logarithm raised to a single power, you can pull that power out and make it a multiplier, a coefficient. So this would be e raised to the natural log of b and then times x, right? Pulling the x out and making it again a factor or multiplier. So now I have e to some function of x, right? E to something. So when you go to differentiate that, remember it's going to be itself, but then times, right? And then the chain rule would be applied, because again, if that's not just x in the power, you have a composition. So it would be itself, then times the derivative of the expression that's in that power. So look, so y prime here, f prime, so would be, an e to something is itself. So e to the natural log of b times x. But then afterwards, times the derivative of the power. And the power, again, natural log of b is a number. That's like 5 or 10, 5x, 10x, 12x. Remember, the derivative of a multiple of x is just that coefficient. So what we're going to multiply by afterwards here is just the natural log of b. And this thing here, this e to the natural log of b times x, that was the original b to the x. All right, so the derivative of, any base to the x power, b to the x power, some exponential with any base, any positive base, is going to be itself. So again, b to the x again, but then after that, you have to also add on this factor multiplied by the natural log of the base. All right, so this is the general rule for the derivative of any exponential function. And hopefully you see that, when the base is e, you'd have e to the x times natural log of e, but the natural log of e was 1, so the derivative of e to the x is just e to the x, as we saw earlier, right? So again, this is more general, more broad for any base that's positive. Okay, so now that we got all these rules, right, I got the derivatives of any logarithmic function with any base, any positive base, the derivatives of all the exponential functions with any base. Now we can go through and do a lot of these problems from the homework assignment. So the first objective I'm looking at here is find the derivative of an exponential function whose base is e. Now they're mixing it up on you, right? It's not just a plain old exponential function. You have something here where I'd have to use the product rule. I'm going to rewrite this fraction as something with a negative power, so that way I can just use the product rule here. And then this exponential is not just e to the x, it's e to something else with x, right? It's e to a function of x, this 3x cubed plus 2x squared. So the chain rule is going to come up here as well. So it's taken a lot of the stuff you did in previous assignments, previous videos, and putting it all together. Chain rule, product rule, quotient rule, power rule, derivatives of trigs, inverse trigs, exponentials, logs, all sorts of stuff being put together here. So here's what I'm given in this problem, right? They're saying, this function called k of x, is 2 divided by x to the 5th times, and then an exponential, e raised to some power. That's not just x though, right? I'll put in parentheses, this is the 3x cubed plus 2x squared power. So like I said, I'm going to rewrite this first factor here. Instead of 2 divided by x to the 5th, I'm going to write that as 2 times x to the negative 5th, right? So there's my first factor when I'm going to go through the product rule. Then times, again, this exponential e to the 3x cubed plus 2x squared power. All right, so again, I'm using the product rule here. So when I go to write out k prime, remember how the product rule goes. So I have two factors, this one with the negative power here, and then this exponential. So I leave one of them alone first. So you got, 2 times x to the negative 5 then times, and then the derivative of my exponential. So remember I said this, if you have e to some power with a variable, the derivative will be itself. So once again, e to the 3x cubed plus 2x squared, but then apply the chain rule, right? Because this is definitely, this polynomial is put inside e to the x, right? There's definitely a composite going on here. Then afterwards, times the derivative of that power, which is a simple polynomial. That'd be 9x squared plus 4x afterwards. 9x squared plus 4x. There's my first factor the way it was. And then this here is the derivative of the second factor with the chain rule applied. Then don't forget, right, plus, and then I do the other way around where I take the derivative of the first factor, which would be negative 10 times x to the negative 6, right, applying the power rule there, times, and then leave the second factor, this exponential, the way it was, e to this 3x cubed plus 2x squared power. And that's it. All right, this here, and for most of these problems, you did, if you watched my last video, this doesn't always work, but for most of these problems, if you're typing in something that's equivalent to their answer, they'll take it. So I'm actually going to type this in, except for here when I do the plus the negative 10, I'm just going to make that minus 10, and then the rest of it. So back here, filling in the blank. So we have 2 times x raised to the negative 5, right? That was the first factor. And then maybe I'll put in parentheses again. So then times, e raised to the 3, that 3x cubed plus, plus 2x squared, all in the power there. But then times the derivative of that power, which was 9x squared plus 4x, right? So that's the first factor times the derivative of the second factor. Double checking that I'm typing everything correctly. All right, then we have plus, negative 10, so minus 10 times x to the negative 6. Then times, the exponential the way it was, e raised to this 3x cubed plus 2x squared power. So this should be good. Hopefully I typed it in correctly. Wonderful. So again, I think, yeah, so they actually rewrote the negative powers as, the reciprocal of the positive ones. They actually multiplied things out too, right? So again, as long as what I have is equivalent to what they have, they should take it. All right, so after you're done submitting an answer, right, you're going to be told that you're correct or you're incorrect and be given some sort of answer explanation. I'd recommend reading through these, whether you got it right or wrong. If you got it right, who knows, maybe they did something in a way that you like better than what you did. And you might want to try that method for questions that are similar in the future. Obviously, if you got it wrong, read through the answer explanations and try to see if you can figure out where you went wrong. And hopefully you can learn from your mistakes for future questions that are similar. All right, so now we're switched over to find the derivative of a natural logarithmic function using properties of logarithms. So again, remember properties of logarithms. This isn't a pre-calc class, all right? So like I'm assuming you remember that the log of a fraction, you take the log of the numerator minus the log of the denominator, right? That was the quotient rule. Log of a product, you can write it as the sum of the log of each factor, Right, that was the product rule, and I already mentioned the power rule a couple times now. If everything inside a logarithm is raised to a single power, you can pull that power out as the coefficient outside. So it says here, right, find the derivative of the following logarithmic function, right? It's the natural log of, some wild expression here, but using the properties of logarithms. So here's what they mean by that. Now you could leave it the way it is without using the properties, and that's fine. It's just, it would probably be a little nastier than you'd like, because here, look, if I had the natural log of, and then something with x, right? It's not just x in here, it's 5x cubed, pardon me, times the sine of negative 5x divided by, 3 minus x. So, I mean, you could just say, hey, the derivative, f prime, remember the derivative of the natural log of something is 1 over that thing, the reciprocal of that thing. So I write the reciprocal of this, 3 minus x in the numerator, divided by, and then 5x cubed times the sine of negative 5x, all in the denominator. But then times the derivative of this expression inside, where I'd have to use the quotient rule. And when I do the derivative of the numerator, I'd have to use the product rule and the chain rule. Like, it would be a little much, but then I would multiply by the derivative of the expression inside and, apply the quotient rule and product rule and chain rule, blah, blah, blah. That would be a little nasty looking, I think. So I'd rather do this, right? I'm going to rewrite f. Okay, so I'm not doing the derivative yet. All right, this is still f. This is still the original function. This is use some properties of logarithms to rewrite the expression. I'll just say properties of logs. So look, I got the natural log of a fraction. So I can split that up, do the log of the numerator. So the natural log of 5x cubed times the sine of negative 5x. And then minus the natural log of the denominator. So the natural log of 3 minus x. And then inside this first log, I've got a product of 3 things. I got 5 as one factor, then x cubed, then sine of negative 5x. So I can use the product property for logarithms, okay? So this is still f. I have not taken the derivative yet. And split this up. This is the natural log of 5 plus the natural log of x cubed, but there's where I can use the power property and pull that 3 out front. Guess I'm just kind of skipping a line here. Or if I had x cubed in here, x to the third, you can apply the power property of logs and pull the power out front. And then finally, there's one more factor in here, plus the natural log of this sine of negative 5x. Okay, and then this last part, all right, this last logarithm here, 3 minus x, that's not a product, it's not a fraction, it's not all raised to some power other than 1. So that doesn't, I can't apply any properties to that log. So that's just going to stay minus the natural log of 3 minus x. All right, so now I've used, all the properties of logs I could. Quotient, power, product. Now I have f rewritten in a nice, as a nice sum. Right? This is a nice big sum. So now I'm going to differentiate. And we'll go just term by term. So f prime is, 0, or the natural log of 5. There's no variable in this. This is a constant. So the derivative of that is 0 plus, and then, 3 times 1 over x. So from this term, I'm getting 3 over x. And that is just plain old natural log of x, right? So if you wanted to use the chain rule, then you would multiply by the derivative of x, which is just 1. And you don't need to write that, right? Times 1. So this is 3 over x. Then plus, and then from this term, now this is not just the natural log of x, it's the natural log of, something with x. So I got to use chain rule here. So this would be 1 over the thing inside. Again, 1 over what's inside. Then chain rule times the derivative of what's inside, where I'm still using chain rule because it's not just the sign of x, it's the sign of, something with x. So times the derivative of the sign of something was the cosine of that thing. So I got cosine negative 5x. And then times again the derivative of the expression inside that, which would be negative 5, right? Derivative of negative 5x. So this is all coming from the second term here. And then the last one, you got minus. Again, the derivative of the natural log of something is 1 over that thing, so 1 over 3 minus x, but then times the derivative of the expression inside. The derivative of 3 minus x would just be negative 1. And I can simplify this a tad. Now, again, if you want to type this in as it is, that should be fine. This should be totally valid, totally acceptable. But I'll go through, the first term there, it's just 3 divided by x. And then this second product, you have negative 5 in the numerator, and now cosine of something divided by sine of that same thing. Remember, that's cotangent, so you could write this as negative 5 times the cotangent of negative 5x. And then this last term, again, I got a negative 1 times a minus out here, so the numerator is positive 1, so I'd have plus 1 over 3 minus x. And this is a nice, a much more clean version of what would happen up here, if I did, again, the reciprocal of the thing inside, then times the derivative of the thing inside with the quotient rule and all that. I think this is a lot cleaner, a lot less typing to do. So f prime, again, after using the properties of logarithms, writing it as a big sum, and then going term by term, we'd have 3 over x minus, 5 times the cotangent of negative 5x, then plus 1 over, and then 3 minus x in that last denominator. Wonderful. Yeah, so they actually took the 3 over x and 1 over 3 minus x and put them together as a single fraction. I don't think that's really necessary, as long as it's equivalent. So now we're just to straight up the derivative of a natural logarithmic function. All right. So again, they're having you combine with other rules here, right? It's not just the natural log of x, it's the natural log of some expression with x inside. And this natural log is itself inside the square root. So I'm going to do power rule first, right? I'll rewrite this as something to a power. So again, they're having you just, don't forget that all the old rules we've learned don't go away. So here's the way it originally looks. You have the big square root. Then inside this, so definitely a composite function, right? The natural log of, and then inside of that, so a composite within a composite. 3x squared minus 2 times x to the minus 1 power, the negative 1 power. So again, the way I'm going to think about this when I go to write the derivative, so again, this is still f. I haven't done the derivative yet. You have this natural log function with, 3x squared minus 2x to the negative 1 inside. And then, square root of all that would be that, raised to the 1/2 power. So now when I go to differentiate, right, remember you work from the outside in with these composite functions, f prime, This is something to the half. So I'll apply the power rule. I'll pull that half out front. So it'll be half of, and then what's inside originally stays inside. So you got, natural log of 3x squared minus 2x to the minus 1 to the negative 1/2, right? 1/2 minus 1. All right, so that's applying the power rule. It took care of that. And keep going with the chain rule here, times the derivative of the expression inside. Now, the expression inside, remember the natural log of something. The derivative of the natural log of something is 1 over that thing. So 1 over, or the reciprocal of that thing, however you want to say it, 1 over 3x squared minus 2x to the negative 1. But then after that, so more chain, right, times the derivative of the expression inside that, which would be 6x, plus 2 times x to the negative second. Applying the power rule to both those terms. And here we go. Now, if you want to simplify this, you can. Half of this term over here, if I multiply the half by this factor, that'll make this 3x plus 1x to the negative half. And I can put this in the numerator here. So I'm going to do that just to save a little typing. So again, f prime. So again, I'm using the half on that other factor. So I have just the natural log of 3x squared minus 2x raised to the negative 1. And then this raised to the negative 1/2. Okay, bring that down. Then times, and again, half of that one factor I mentioned was, 3x plus, and then 1x to the negative 2 power. And then divided by, right, you had this 3x squared minus 2x to the negative 1 in the denominator. 3x squared minus 2x to the negative 1 power. Okay, so this should be good. Great. So let's see how they wrote it. Yeah, so they wrote it in another way, but again, as long as what I have is equivalent to what they have, it should be taking it. And if it doesn't, send them some feedback. All right. So back to this one with the properties of logarithms. So again, here's the function the way it originally looks. We have the f of x equals the natural log of, and then an expression in here that I can split up using properties of logarithms. You got 9 times x to the 4th times, and then the square root of 5x minus 3. All right, so I'm going to go through here. Now this is still f. All right, this is still the original function, just rewritten using the properties of logarithms. So it's a product, and while I'm doing the product, I'm also going to pull some powers out. So we have the natural log of just, the first factor, 9, plus the natural log of the second factor is x to the 4th, but I'll pull that 4 out using the power property. So that turns into 4 times the natural log of x. Then another product, another factor, plus, then we have the natural log, and then this, remember, square root is to the half power. So this is 5x minus 3 to the half power. I'll pull that out front, using the power property for logarithms. And there, that's all the properties I could have applied there. And now I go term by term and find f prime. Right, so I am now differentiating, right? This is now the derivative. Natural log of 9, that is a constant, right? There's no variable, there's no x in this, so it's a constant. The derivative would be 0. Then this term here would be 4 times 1 over x, so 4 over x. And then this term here would be plus, 1/2, and the coefficients stick around, a half. And the derivative of the natural log of something is 1 over that thing, so 1 over 5x minus 3, and then times afterwards the derivative of that thing. The derivative of 5x minus 3 is 5. All right, so if I put some stuff, let's multiply this out a little bit, just to save on some typing. We have 4 over x plus, and then the numerators here make 5. And if I multiply the denominators, you'd have 10x minus 6. 2 times 5x minus 3, right? And this is what I'm going to type. That'll be a short one to type. There's your derivative function. And it's a lot nicer than writing, the reciprocal of this multiplied by the derivative of this, because then I'd have to use the product rule, and while it'd just be a mess. You could still do it, but it would be a mess. So we have 4 over x plus, and then 5 divided by, 10x minus 6. And this should be good. Right. Yeah, they actually put them together, get a common denominator and put them together. Again, you don't have to do that. All right. All right, so this one has, once again, we're doing lots of chain rule stuff here. So it's not just the natural log of x. You got this 3 minus 4x inside the natural log. But then the natural log is, multiplied by 3 and put inside this cosine function. So I'm working from the outside in here. The first thing I'm doing the derivative of is the cosine of something. Right? And I keep applying the chain rule. So here's the way it looks. F of x equals, again, the cosine of, and then 3 times the natural log of, and inside the natural log is this 3 minus 4x expression. So derivative, and working from the outside in, there's definitely composition here. I see the cosine of something. Remember, the derivative of the cosine of something is the opposite of sine or negative sine, with that still inside, right? So with 3 times the natural log of 3 minus 4x, still inside this sine. All right, then chain rule, all right, keep going. Times, and then the derivative of the expression inside would be 3 times 1 over, so 3 over 3 minus 4x. But then still, right, because that was the natural log of something, is 1 over that thing. But then after times the derivative of the expression inside that, which would be negative 4. All right, so again, just to save on some typing, you have a negative coefficient out here, negative 1 times 3 times negative 4. So you have positive 12 in the numerator with this, sine of 3 times the natural log of 3 minus 4x. And your denominators are just this, the only denominator in any of these is 3 minus 4x. So this is what I'll type in. Numerator 12 times the sine of 3 times the natural log of 3 minus 4x divided by, and then 3 minus 4x. Great. Oh, that's exactly what they had. Wow. Okay. So another one where it's not just e to some x power, it's something where I'm going to have to apply the chain rule, right? It's e to something. But remember, the derivative of e raised to some power with a variable is itself then times the derivative of that power. Okay, so here we have k of x is, again, e raised to this power, this negative, x to the negative 1/5 power, then minus, 5/4 times x to the negative 1/2 power. So when I do the derivative, right, k prime, so I've been saying a little, I said it a little bit with exponentials with base e. the derivative of an exponential with base e is itself. So I'm just writing this again, the very same thing again. But then chain rule, right? Because that's not just x up there, it's this polynomial or this expression with rational powers put in here. So I gotta multiply by the derivative of that power, the thing inside the power, which I would just go term by term power rule here. So it'd be positive 1/5 times x to the negative 6/5, right? Negative 1/5 minus 5/5, negative 1/5 minus 1. And then the next term, I'd have positive 5/8, so plus 5/8 times x to the negative 3/2, right? That'd be negative 1/2 minus 1, negative 1/2 minus 2/2. And this is it. This is again, itself times the derivative of the power, applying the chain rule to an exponential. So I'm typing all this in. So e raised to the, make sure all this is in the power, negative x to the negative 1/5 power. Get down a little bit, and then minus 5/4, still in the power, x to the negative 1/2, all that in the power, times, so in parentheses, the derivative of that power was, 1/5 times x to the negative 6/5 power, then, oops, got the power, plus, and then 5/8 times x to the negative 3/2 in the power there, and close the parentheses. Oops, close the parentheses down here. That should be good. All right. So there's one again where I'd have to go through and do the product rule. So again, it's not just the log of x, it's the log of, something else with x in it. So chain rule is going to come into play when I differentiate that factor. And then you got a first factor here of negative 2x to the negative third. So again, going through the product rule, writing this out. So here's the way it originally looks. So again, I'll put this in parentheses. Here's my first factor, negative 2 times x to the negative 3 times, and then the other factor, natural log of x plus x to the negative 1. So again, product rule. So f prime, leave the first factor the way it is, so negative 2 times x to the negative 3, then times, remember it's 1 over, the derivative of the natural log of something is 1 over that thing, but then times the derivative of the thing inside, right? I keep going, the chain rule here. The derivative of x plus x to the negative 1 would be 1 minus x to the negative 2, right? Applying the power rule to both of these. All right, so that's the first times the derivative of the second, then plus, and then the derivative of the first using the power rule right here would be positive 6x to the negative 4 power. And then leave the second factor, the way it was, the natural log of x plus x to the minus 1. And this is good here. I might multiply this and this, right? This with this factor here, or just put them both in the numerator. Okay, so let's type this out. So that first product in the numerator, negative 2, well, make sure it's in the numerator, put in parentheses, negative 2 times x to the negative 3 times, the other factor up there would be 1 minus x to the negative 2. All right, so all that up top, and the denominator of x plus that x to the minus 1. All right, so that was the first product, first term. I just leave the first alone times the derivative of the second. Then plus, derivative of the first factor, 6x to the negative 4 times the second factor the way it was, natural log of x plus x to the minus 1. or -1. This should be good. Great. And again, the way they rewrote it is different, but it's still equivalent to what I had. All right, so another one where now you can rewrite this instead of dividing by -x, because if I leave it this way, I'd have to use the quotient rule. It's a fraction, but you could rewrite divided by -x as times, -x to the -1, which I think I will do, so that way I can just use the product rule again. So again, here's the way it originally looks. You have the numerator with this natural log of, and then, not just x, but something inside here. So chain rule is going to come into play when we differentiate this. So -2x cubed plus 5x squared in here, and then divided by -x. But like I said, I'm gonna rewrite this instead of dividing by -x. I'm gonna write that as times, -x to the -1. That's the same thing. And then times this natural log of -2x cubed plus 5x squared. And then go through and do the product rule, right? You can do the quotient rule with the original, but if you rewrite it this way, you can go through the product rule. So f prime, leaving the first factor the way it is, times, and then the derivative of the second factor. Now again, natural log of something is 1 over that thing. So 1 over -2x cubed plus 5x squared. But then, I'm going to put it up top here, multiply, numerator be 1, but then I'm going to multiply by the derivative of the expression inside. So the numerator now has -6x squared plus 10x. So again, we can simplify this by factoring out x's and whatnot. I'm just not gonna do that. So there's, first times the derivative of the second, then plus, and then the derivative of the first factor will be positive x to the -2nd. And then leave the second factor the way it was, times the natural log of -2x cubed plus 5x squared. All right, now I'm just going to leave this. I might distribute this actually, just to save on typing, make this, positive 6 times x, and then -10 in the numerator there. So that first term as positive 6x, then -10 over, and then the -2x cubed plus 5x squared. Then after that, plus, the x to the -2nd power times the natural log of this -2x cubed plus 5x squared. And this should be good. Right. So this one's just this is just a straight up product rule one. Now the nice thing about this one is the factor that has natural log of x is just natural log of x, right? Not the natural log of some crazy expression with x. But still, it is a product. I have this, first factor with the -2x plus 3x to the -2, and then second factor of natural log of x, right? So I'm just gonna got room here. Stop wasting space. So we're given this function. So the first factor is this -2x plus 3 times x to the -2 times, and second factor is, natural log of x. All right, so when I go through the derivative, I'm using the product rule, right? So remember, I leave one factor alone. And then times, and the derivative of the second factor is just, 1 over x, or x to the -1. And actually, I'm going to distribute that to make that a little nicer to type. All right, then plus And then the derivative of the first factor would be -2, and then minus 6x to the -3. And then times, leave the natural log, the second factor, the way it was. So again, I'm going to distribute this and make this, -2 plus, and then 3x to the -3, because again, this is the same thing as x to the -1 here. So, all right, so the first term is just -2 plus 3 times x to the -3, right? So that was the first stuff. Then plus, and then the derivative of the first factor, -2 minus 6x to the -3. But then times, natural log of x. That, yeah, that should do it. Great. All right, so that objective's done with the natural log stuff there. So still more natural log, but this is that using the properties. So this is very similar to a question from earlier. All right, I'm just gonna tell you what it simplifies to after using properties, right? So f of x is the natural log. So here's the way it originally looks. So you got 4 times x to the 4th times, the sine of -7x up top, divided by, and then 3x minus 3 on the bottom. So if I use properties of logarithms, right, this is still f, right, it's still the same thing. I'd end up with this. You have natural log of 4 plus 4 times the natural log of x plus the natural log of the sine of -7x, and then minus the natural log of 3x minus 3. And you could factor the 3 out, make that a product, and split it up more, but I don't feel like it. This is good. Now I'll differentiate. All right, use the properties of laws to get this, and then we'll go one term at a time, find the derivative. First term is a constant, so the derivative is 0. This term here would be 4 times 1 over x, so just 4 over x. Plus this term here would be, again, 1 over the sine of -7x. But then times the derivative of that would be the cosine of -7x times -7. Right, applying the chain rule a couple times there. And then this one here would be minus, again, 1 over the thing inside, 3x minus 3, but then times 3, right, times the derivative of the numerator, which if you were to factor 3 out of the bottom, that would just turn this into 1 over 1x minus 1. And this here I'm going to call, cotangent, again, of -7x. All right, so we have 4 over x minus 7 times the cotangent of -7x, and then minus 1 over x minus 1. That's what I'm typing in. That should be good. Yeah, I think they probably they put the fractions together, the rational expressions together again. You don't have to. All right, so another one of the properties ones. All right, so again, like the last one, I'll just write it out as it originally looks, and then I'll just jump to the part where I get, use all the properties, write what it would simplify to or expand to if I used all the properties I could for logarithms. So here's the natural log of, and then inside here, this is the 4th root of x minus 2 divided by, 5 minus 10x. So again, I would pull the 1/4 out of everything. So we'd have 1/4 times in the natural log of this fraction, which I would do natural log of the numerator minus natural log of the denominator. And that would be about it. Now you could factor 5 out of these and split it up even more, but again, this should be good enough. And if you want to put the 1/4 in, you could, but now let's differentiate, right? So here's f prime. So again, it'll be 1/4 times, and then 1 over x minus 2, times the derivative of x minus 2, but that's just 1 again, then minus, and then the derivative of the natural log of something is, 1 over that thing. So you got 1 over 5 minus 10x, but then times negative 10. All right, so I'll put negative 10, the derivative of 5 minus 10x is negative 10. That goes in the numerator there. Yeah, and I can type this. I'll turn this into plus 10. So we got 1/4. I'm just going to keep that on the outside, and 1 over x minus 2, and then plus 10 over 5 minus 10x. Close all those, right? The quarter on the outside. If you want to distribute the quarter, you could. This should, yeah, that should be good. Great. And back to the ones with e's involved. All right, so this is definitely one where I got to use the chain rule. All right, it's not just the cosine of x, it's the cosine of, and then this, exponential function in here. Cosine of an exponential 4 times e to the negative 8x power. So, right, when I do the derivative, remember the derivative of cosine of something was negative sine of that thing. So I still have negative sine of, 4 4 times e to the negative 8x, but then afterwards, chain rule, multiply by the derivative of the expression inside, which would still, have 4 times e, it'd be 4 times, and then remember the derivative of exponential is itself, so e to the negative 8x, but then times the derivative of that power, the derivative of negative 8x is negative 8. And if you want to put the coefficients all together, the number factors, you got negative 1 times 4 times negative 8, that'd be positive 32 for the coefficient. And then times this, sine of 4 e to the negative 8x times e to the negative 8x. And this is what I'll type in. So positive 32 times the sine of 4 times e to the negative 8x power, and then times e to the negative 8x power outside that. All right, then here's one where, now again, if you want, I could rewrite this so I can use the product rule. I'll use the quotient rule. What the heck, I haven't done it yet in this video, so let's go through and do the quotient rule on this one. So I'll leave it as a fraction. Got, k of x equals, and I'll put that negative up top. So you have negative, e to the negative 2x cubed power in the numerator, and then 4x to the fourth in the denominator. So I'm going to, again, you can rewrite that as, 1/4 times x to the negative 4, but then use the product rule. But I'll go through and do the quotient rule. So we got k prime. Remember the quotient rule, you got the, leave the denominator the way it was, 4x to the fourth times the derivative of the numerator. Now the numerator is exponential, so it's going to be itself negative, e to the negative 2x cubed, but then chain rule, right, times the derivative of the power. The derivative of negative 2x cubed would be negative 6x squared. Right, so that's all the first term up here. And then you got minus, and then the derivative of the denominator would be 16x cubed times, and leave the numerator the way it was, negative e to the negative 2x cubed. And then all that divided by the denominator, squared. And if you want to simplify some things, you can. Like the coefficient on this first term here would be positive 24, and the coefficient on this second term would be positive 16. So I'll write that. Okay, so up top, we got positive 24. And then there was an x to the fourth and an x squared, so that's x to the sixth. And then you have your e raised to the negative 2x cubed power. All right, so that was the first term put together up top, multiply all the factors together. And then plus 16x cubed times e to the negative 2x cubed power. All right, so this is the entire numerator. And the denominator, if I were to square 4x to the fourth, that'd be 16x to the eighth. And that should be good. Now they might have divided each of these by 16x to the eighth or whatever, but again, as long as it's equal to their final result. Yeah, so they did some factoring and simplifying, but same thing. All right, so here's a product rule one, right? You got first factor. Now the nice thing is the first factor is just e to the x. All right, so derivative of that will be no problem. But then you have times this other factor with the powers of x here. So I got to go through the product rule with these two factors. All right, so we're given k of x equals e to the x times, and then negative x to the 2/3 minus 4/3 times x to the negative 3/2. So again, going through the product rule here, and leave the first factor alone, e to the x times, and then the derivative of the second one is, a couple power rule for each term. So it'll be negative 2/3 times x to the negative 1/3, right? 2/3 minus 1, 2/3 minus 3/3. And then power rule here would be positive, 2, right? 12/6, so plus 2 times x to the, negative 3/2 minus 1 would be negative 5/2, right? Negative 3/2 minus 2/2. All right, and then plus, and then the derivative of the first is just e to the x again. All right, the derivative of e to the x is e to the x. Times, and leave the second factor the way it was, this negative x to the 2/3 power, then minus 4/3 times x to the negative 3/2. And this is what I'm typing. Now you could factor e to the x out of both of those, but I'll write it. So you have the first factor, e to the x, times, and then, negative 2/3 times x raised to the negative 1/3 power, plus 2 times x to the negative 5/2 power. All right, and then plus, e to the x again, times, and then the second factor the way it was, the opposite of x to the 2/3, minus 4/3 times x to the negative 3/2. All right, so this should be good. Yay. Okay, so that first set of objectives is done. All right, if you look back at the activity log, I'm done with that group where everything was base E. So now we're working, when the base is not E. So I had those rules up, early on in the video before I did any questions. Remember, the derivatives of logs and exponentials when the base wasn't E is very similar to when it was E. You just had to have that natural log of the base factor in there somewhere. You'll see. All right, so this is simply find an actual value. All right, so find the derivative, find the slope of the line tangent to the graph of this at x equals 4. So, I'm actually going to do properties of logs here too. Rewrite this, make it a little easier on myself. So here's what we're originally given. Got log, base 8 of 3x minus 4 divided by 2x plus 3. And look, I'm using properties of logs. This would be the log base 8 of 3x minus 4 minus the log base 8 of 2x plus 3. And we're asked to find the derivative, add x equals 4. So let's find the derivative first. So remember, the only difference between this and the natural log was, it was still the same starting value. The derivative of the log of something is 1 over that thing. So you got this 1 over 3x minus 4. But then also in the denominator, you need this factor of the natural log of the original base, right? So the natural log of 8 is also down there. Then minus, and then same thing here. Oh, and then times 3. Sorry, times 3, because then the expression inside is not just x, is 3x minus 4. So then I got to multiply by 3, chain rule. All right, so this would be 3 over this 3x minus 4 times the natural log of 8. And then similarly here, that'd be 1 over 2x plus 3. But then down here with the 2x plus 3, you also should have a factor of the natural log of 8. Then times 2, right? Times the derivative of the expression inside, and that'll put 2 in the numerator. So here's the derivative at any x. So at x equals 4, I'm just putting 4 in for x here. We'd have 3 over the natural log of 8 times, and then 3 times 4 is 12. 12 minus 4 is 8, so that's 8 log 8 down there. Minus, and then 2 over, again, the natural log of 8 in the denominator times, and then 2 times 4 is 8, plus 3 is 11. And there you go, whatever this value is. And they say enter an exact answer, right? So enter it as is. I might put the 8 in front of the log and the 11 in front of the log in the denominator there, but this is it. Okay, so the derivative at 4 is, 3 divided by 8 times the natural log of 8. Then minus, 2 divided by 11 times the natural log of 8. So again, whatever that value is, that will be the slope of our tangent line to the graph of this thing at x equals 4. They actually got a common denominator and put it all together, but again, you don't have to. All right. So another one with properties of logs. So again, this is log base 3. All right, so I'm going to do everything I did with natural log, but just remember to put the natural log of 3 as a factor in the denominators of the derivatives. So the way it originally looks. Got log base 3 of, and then this x to the 5th times the cosine of 3x in the numerator and 1 minus 9x in the denominator. So again, I'm going to use properties to rewrite this. This would be rewritten as 5 times the log base 3 of x plus the log base 3 of the cosine of 3x, and then minus the log base 3 of 1 minus 9x. And then I'll go term by term. All right, so f prime. And this will be 5 times 1 over x, but then you got the natural log of 3 down there with the x as well. So x times the natural log of 3, or natural log of 3 times x. All right, then plus, and then again, 1 over the cosine of 3x, but times the natural log of 3. And then times the derivative of the cosine of 3x, which would be negative, now I'll put this in the numerator, negative sine of 3x, and then times the derivative of 3x. So I'll throw 3 up here too. So I got -3 sine x, -3 sine of 3x over the natural log of 3 times the cosine of 3x. And then finally here minus, and 1 over 1 minus 9x, but still times this natural log of 3 down here. Then times the derivative of 1 minus 9x, which would be -9. So let's make the numerator -9. Actually, I'll make it +9 because of this minus minus. And honestly, so I don't have to keep typing log 3, log 3, log 3. I'm going to factor this out. So it'll be 1 over the natural log of 3 pulled out, and then a bunch of the other stuff left over in here. All right, so you'd have 5 over x. And then this would just be -3 times the tangent of 3x. Right, sine of 3x over cosine 3x, and then +9 over 1 minus 9x. All right, so again, just so I don't have to keep typing it, I'm going to pull out this 1 over natural log of 3. All right, so derivative, again, 1 over the natural log of 3 pulled out, and then in parentheses the rest of it, 5 over x, then -3 times the tangent of 3x, plus, and then 9 over 1 minus 9x. Close the parentheses. That should be good. Again, look at how they had it, where they kept the natural log of 3 down there in every single term. I just factored it out and rewrote sine of 3x over cosine 3x as tangent 3x, right? So same thing. All right. Honestly, I mean, okay, you could keep it this way, but then when you do the chain rule, right, when you take the derivative of the thing inside, you'd have to do the product rule. But since there's only the two factors here, I'm going to multiply this out, and that way I won't have to do the product rule when I apply the chain rule. So again, here's how it originally looks. Got the log base 4. Actually, no, you know what? I'll just use properties. I know it's not that particular objective, but I'll just use properties. So we have -1, times the quantity x plus 4 times, and then 3x minus 1. So again, you could multiply this out pretty easily, but if you went through the properties, I'm gonna put this minus with this factor. I'm gonna multiply that by -1, make this 1 minus 3x. So then I split it up, do the log base for the first factor, the first product, then plus, the log base for of, the opposite of 3x minus 1, so 1 minus 3x. And now I'll just go term by term here. So again, this would be 1 over x plus 4, but then times that natural log of 4 down there, then plus, and then here you have 1 over, 1 minus 3x, but still, times the natural log of the base, natural log of 4 down here, but then times the derivative of 1 minus 3x, which would be -3, so I'll turn the numerator up here into -3, which I'll just make that -3. And like I did before, I'm going to factor out this 1 over log 4, so I don't have to type it twice. So derivative is 1 over, the natural log of 4 times, and then in parentheses, what would be left over if I did that? 1 over x plus 4, and then -3 over 1 minus 3x. And that should be good, equivalent to what they have anyway. Right. All right, so now we have exponentials with bases. These are some base 10 ones. And this is one where I kind of have to use the quotient rule. Now I could turn this into, times the quantity 10 to the x plus 4 and then raise that to the -1, turn it into a product rule thing, but I will just leave it this way and do a quotient rule. So this has some exponentials base 10. So you got f of x equals, numerator is 10 to the x power. The denominator is 10 to the x power, but, plus 4. So I'm doing quotient rule. So denominator, so f prime, got denominator the way it was, 10 to the x plus 4, times, now remember the derivative of the numerator, this has been a bit since the beginning, early on in the video, but remember the derivative of an exponential is itself, so 10 to the x, but then times the natural log of the base. So I also have to have this times natural log of 10 here. So there's the denominator times the derivative of the numerator, then minus, and then the numerator times the derivative of the denominator would be the same thing, right? Plus 4 would have a derivative of 0, so it's just 10 to the x times that natural log of the base again, 10 natural log of 10. Right? And then all that divided by, the denominator, 10 to the x plus 4 squared. Now look at this. If I took this 10 to the x times natural log of 10 and distributed it, we'd get 10 to the x, squared times natural log of 10, and that's what's going on over here too. So those are going to subtract away, and I'm going to be left with, just 4 times 10 to the x times the natural log of 10 in the numerator. That's all that's left. And then this 10 to the x plus 4, squared in the denominator. So here's what I'm going to type, just a little simpler, a little less typing. So f prime, again, numerator has this, 4 times, 10 to the x power times the natural log of 10, right? So that's the numerator. And then denominator is this quantity, 10 to the x power, plus 4, all squared. And that's pretty much exactly what they had. They just had a rearrangement of the factors up top, but it's the same thing. So this one, you got another composite, right? So it's the sine of something, but that thing inside there is an exponential with a base 2. So I'm going to be using the chain rule here as well. So given f of x equals, the sine of, and then an exponential, 2 to the 6x power. So, I'm going through the derivative, working from the outside in. From the derivative of the sine of something will be the cosine of that thing. All right, then times the derivative of the expression inside. So remember, the derivative of an exponential is itself. So 2 to the 6x again, but then times the natural log of the base. So there's a rule for any exponential. But then, going further inside, that power is not just 2 to the x, it's 2 to the 6x. So then times the derivative of 6x, which would just be, 6. Keep going with the chain rule there. So let's type this. This should be fine. So we have the cosine of this 2 raised to the 6x power times, and then the derivative of 2 to the 6x would be 2 to the 6x times the natural log of 2 times 6. And this should be good. And they throw the 6 out front, but same thing. So once again, asked to use some properties of logarithms to, rewrite this. Okay, So let's do that. So here's the original. Got the log, base 3 of, and then negative 2x, to the 5th power times the square root of negative 6x minus 1. All right, so I'm going to use properties to rewrite this. Now I'm going to think of this as negative 32x to the 5th. I'll keep it that way actually, because I don't want to confuse people by having a negative number inside a log. And yeah, so let's leave it this way. So I'll do the product rule and then, pull the power of 5 out. And then this negative 6x minus 1 is to the half power, right? So I'll pull the half out. So this is 5 times the log base 3 of negative 2x. And x would have to be some negative number here to make the expression inside positive. Whatever, right? And then plus product rule, and then again pulling the half out of that other one. Half times the log base 3 of this negative 6x minus 1. All right, so now that I've applied some properties here, split it up, let's go through term by term, take the derivative. So this first one would be 5 over the negative 2x. But then don't forget the times, natural log of 3 down here, because it's not log base e, it's log base 3. And then times the derivative of the expression inside, so times negative 2 after, which would make this numerator negative 10. I'll write that in a second. Or you could cancel the negative 2's. See the negative 2 numerator, negative 2 in the denominator. You can cancel those factors. Then we have plus, 1/2 times, 1 over negative 6x minus 1. And don't forget the times natural log of 3 down here. This is log base 3, so natural log of 3 factor down here as well. But then times negative 6 up top, right? The derivative of the expression inside. So like before, both of these have this 1 over natural log of 3 inside, so I'm going to pull that out. And if I do that, what would be left over would be 5 over x in the first term. And then here, half of negative 6 is, negative 3. So it'd be minus 3 over this negative 6x minus 1, which if you want to multiply that by negative, you could turn this into plus 3 over 6x plus 1. So I'm going to type this. So pulled the 1 over natural log of 3 out, just so I don't keep typing it. Times, and then parentheses, 5 over x plus 3 over 6x plus 1. Should be equivalent to what they have. Okay, great. And then look at that, they have this thing here. All right. Okay, so now we're asked to find a specific derivative again, right, at a specific value. So got a log base 3 going on here, and they're saying enter an exact value again. All right, so whatever I get, just enter that. You don't have to go to a calculator and round or anything. So this is f of x equals, and we have the log base 3 of some polynomial inside, right? There's 5x cubed minus 3x squared minus 6. So first let's take the derivative at any x. So again, keep up the general rule for the derivative of any log. The derivative of a logarithm of something is 1 over that thing, right? So I'm putting the quantity, this polynomial 5x cubed minus 3x squared minus 6 in the denominator here. But then don't forget to multiply that by the natural log of the base, right? So there's this factor of natural log of 3 also down here in the derivative. Then times the derivative of the numerator, right, which I'll just put up top. This is going to be times 1, right? So the derivative of the numerator is 15x squared minus 6x, and then plus nothing. All right, so there's my derivative function. And then we're specifically asked for the derivative at x equals 3. So I'm plugging 3 into all these, and we'll simplify. So we got 15 times, 3 squared minus 6 times 3 in the numerator, and then natural log of 3 times, and then in the quantity here, 5 times 3 cubed minus 3 times, 3 squared minus 6. All right, factor 3 out of these, and then you'd have 3 times 15, 45 left over there, minus 6 there. 45 minus 6 is 39. And I'll leave that factored for right now, because I want to see what this is. Now from these two, if I pulled out 3 squared, you'd have 5 times 3 still, so 15, and then minus, no, I can actually pull out 3 cubed, because that's 3 cubed, that's 3 cubed, then you'd have 5 minus 1, 4 left over, so this is 27 times 4, but then minus 6, 27 times 4, 80, and 28, so that's 108 minus 6, that's 102, which is 2 times 51, so these don't have any common factors, so my numerator is 3 times 39, which is 90, and 27, that's 117 in the numerator, and then again 102 times the natural log of 3 in the denominator. There's the exact value, right, without actually punching anything into a calculator and rounding. That would be the slope, whatever this value is, would be the slope of the tangent line to the graph of this log curve at the point where x equals 3. So again, 117, I hope I did that correctly, 102 times the natural log of 3 in the denominator. Wonderful. All right, so I guess they do. Oh yeah, they do have a common factor of 3. My bad. Yeah, 102 is 2 times 51, which is 3 times 17. All right, so my bad. They did have a common factor of 3, but still, what I typed in was equivalent to what they had, so it's good. All right, then we have another log with something other than x inside, right? So I gotta go through chain rule. This is the log base 3 of, and then the secant of, and then 2x, right? So it's, composition within composition here. I'm going to do the chain rule a couple times. All right, so f prime, and is the derivative of the log of something is, 1 over that thing, so 1 over the secant of 2x. But then don't forget that natural log of the base down here as well, natural log of 3. All right, then times the derivative of the secant of 2x would be secant 2x times tangent 2x, right? The derivative of secant was secant tangent, but then multiplied by the derivative of the thing inside that, which is 2. And you see the secant of 2x cancel in here, so I end up with 2 tangent 2x in the numerator and just the log 3, natural log of 3 in the denominator. Okay, so numerator after simplifying would be 2 times the tangent of 2x, and then divided by just that natural log of 3 in the denominator. Wonderful. All right, so another thing with properties. I'll write out the original. It's pretty similar to ones we've seen. but this is log base 2 now, right? So I got to remember to put that natural log of 2 factor in the denominators of the derivatives. All right, so this is log, base 2. And then this time, because it's positive, I'll actually multiply it out. Okay, so 2x to the 5th. This is 32x to the 5th. So that's that factor there. Times the cosine of 7x divided by x minus 8. All right, so I'm going to use the properties of logarithms. So we have the log base 2 of 32. That would be 5 plus, and then 5 times the log base 2 of x, then plus the log base 2 of the cosine of 7x, and then minus the log base 2 of x minus 8, right? That's just expanding this, the properties of logarithms. All right, then the derivative. So 0 and then 5 over x times the natural log of 2 in the denominator. So 5 over natural log of 2 times x down here. Plus, then this one, you'd have, again, you'd have that 1 over cosine 7x. But then again, the natural log of 2 down here with the cosine of 7x times, and then the derivative of cosine of 7x would be negative sine of 7x, and then times the derivative of 7, right? You keep working your way inside with chain rule. And then this last term, just be minus, and then 1 over, x minus 8, and then that times the natural log of 2, and then times 1, so that's it. So again, like I've been doing, this sine x divided by cosine, sine 7x divided by cosine 7x, I'm going to rewrite that as tangent 7x in the numerator there, and factor out the 1 over log 2 from all these, again, just so I don't have to type it up 3 different times. So if I were to do that, got 1 over the natural log of 2 pulled out, parentheses, and then what's left over when I remove all that is 5 over x from the first one and minus 7 times the tangent of 7x, right? This was the sine of 7x over cosine 7x. And then you had minus 1 over, and then if I remove the natural log of 2, you just got x minus 8 in that last denominator. So again, this should be good. Great. So more properties. But this is log base 5, right? So I'm going to end up with a natural log of 5 as a factor in each denominator of the derivative I write. So once again, here's how the initial thing looks. It's the log base 5 of, and then it's a big cube root, and then a fraction inside that, negative 7x minus 5, divided by, negative 2x minus 2. So if I go through and use properties of logs, where I would pull the 1/3 power out, right? This is all the 1/3 power times, and then you have the log of a fraction, which I can split up, do log of the numerator. Sorry, this is log base 5 of the numerator minus, the log base 5 of the denominator, negative 2x minus 2. All right, so now I can go through, do the derivative, right? F prime is going to be this 1/3 times, and then, derivatives of logs are, 1 over what's inside with that factor of the natural log of the base in the denominator. So I got this natural log of 5 down here as well. But then times the derivative of the thing inside, so that'll put negative 7 up top. Then minus, once again, 1 over the expression inside, negative 2x minus 2. But still times this natural log of 5 down here, and then, times negative 2 up top. And if you'd like to just multiply top and bottom by negatives, I'll turn everything plus. So you got 7 over 7x plus 5, 2 over 2x plus 2 with the minus in here. And I'm going to pull out the log 5 again. So we'd have 1 over, 3 times the natural log of 5 on the outside, and then whatever's left over inside here. And this is what I'm going to type. So outside, you got 1 over 3 natural log of 5. Factored all that out. And then the stuff left over, after multiplying the top and bottom of each fraction by -1, you got 7 over 7x plus 5. And then still minus in the middle and multiplying that second fraction on top by -1 and bottom by -1. 2 over, actually, if in fact, I factored the 2 out, you'd have 1 over x plus 1. Right, it's 2 over 2x plus 2, but if you pull 2 out of the bottom, that'd be 1 over x plus 1 when even further simplified. Okay, great. And they got something more involved than I had. All right, now comes, this is one where I'm going to be using the product rule. So first factor is this -2x cubed. The second factor is this exponential. See, I got a base of 8 raised to some, power with a variable, but it's not just x. It's not just 8 to the x, it's 8 to something, so something with x. So I got to use chain rule when I differentiate that. Just don't forget when you differentiate an exponential, it'll be itself, times the natural log of the base and then times the derivative of the power, right, with the chain rule going on. But I got to use the product rule here too, right? Because this is a product of two factors. So our function and first factor is this, -2x cubed. And then the other one is this exponential, 8 to the 7x to the -1 power. So applying the product rule, and I'll leave the first factor the way it is, -2 times x cubed. And then the derivative of the second factor, again, it's an exponential, so it'll be itself 8 raised to the 7x to the -1 power times the natural log of its base, then times the derivative of the power, which I'd apply the power rule to that. That'd be -7x to the -2. Okay, so there's the first times the derivative of the second, plus, and then the derivative of the first is -6x squared, and then leave the second factor the way it is, times this 8 to the 7 times x to the -1 power. Right, and if I want to do the coefficients here, the first term you have -2 and -7, so that'll be +14 out front, and then this will be minus 6, plus -6. Again, 8, this is not a coefficient, it's raised to a power. So I'm typing that out. So again, the coefficient of that first term would be +14. And then there was x cubed along with x to the -2nd. So if you multiplied those, that'd just be x to the first. So 14x, got that factor of the natural log of 8, and then the exponential, right? So times, and then you had that 8 raised to the 7x to the -1 power. All right, so this was the first product put together. And then plus, -6x squared, so -6x squared times the exponential again, right? So times 8 raised to the 7x, to the -1, 7 times x to the -1 power there. All right, so that should be good after applying the product rule and chain rule and all that. All right. All right, so here's another one where I'd go through the product rule, right? One of the factors is 7 to the x power, an exponential function. And the other one I can rewrite, I'm going to rewrite 2 over x as 2 times x to the -1, or 2 times x to the -1. But still, this is going to be another product rule thing. So f of x is, again, first factor is 7 to the x power. And then the other factor in this product is, -6x plus, and then 2 divided by x. But again, I said, dividing by x is the same thing as multiplying by x to the -1. and then I'm going to go through and do the product rule. All right, so f prime, again, I leave one factor the way it is, so this 7 to the x, right, I'll leave that the way it is, times, and then the derivative of this second factor, applying the power rule here, you have -6, and then -2 times x to the -2. All right, so there's first times the derivative of the second, then plus, and then the derivative of the first would be 7 to the x times the natural log of 7. Right, and that's just the x power, so you could write times 1 if you wanted, but that's it. And then times, leave the second factor the way it was, this -6x plus 2 times x to the -1 or -1 power. That's what I'm typing. Okay, so going through the product rule, 7 to the x power times the quantity, -6, then -2 times x to the -2, then plus, and then another, 7 to the x times the natural log of 7 times, and then the way the second factor already looked, -6x plus 2 times x to the -1 power. That should be good after applying the product rule. Good. All right, so here's another one where it's exponential, but again, it's not just 7 to the x. It's 7 raised to some function of x, right? So I got to use the chain rule here. So I'll just keep this same page. So here's f. It's 7 to, this expression up here, -4x plus 1 plus 2 times x to the -1 power. So again, the derivative. And the derivative of an exponential function is itself. So I'm writing it again. Same thing, but then don't forget, the times the natural log of the base, then chain rule multiplied by the derivative of that thing inside the power, which would be -4, -2 times x to the -2. So this is what I'm typing. So again, you got just writing the original the way it was, 7 to the -4x plus 1 plus 2 times x to the -1, then times the natural log of 7, and then times, the derivative of that power, which again was the quantity -4 minus 2x to the -2 power. All right, there's your derivative function. Okay, great. All right, so that takes care of all of the derivatives of exponential and logs with any base and with base e objectives. All right, so the last two objectives are on a particular procedure called logarithmic differentiation. All right, now this is a process, a procedure for finding derivatives, and you can use this to help you find the derivative of any function. But more specifically, it'll be useful when you have a variable base with a variable exponent. All right, so this logarithmic differentiation procedure that we're about to go over, and I'll write the steps up as we go through an example. We'll just go through one of the exercises. So again, what we're about to do is called logarithmic differentiation. So again, you can always use this, but it's most useful when differentiating, finding the derivative of, say, f of x equals, and then you have a function of x in your base to a function of x in your power. All right, so where both the base and the exponent. So again, we're both base and exponent vary, have a variable, have variables. Right? Because if both the base and the exponent have variables, for example, say y equals or f of x equals, just x to the x power, right? That's something like that. This is not exponential. An exponential had a number base and a variable power, like, 2 to the x, e to the x, right? These were exponential. And you can't use the power rule either, right? A power rule had variable base to a number power, like x squared or x to the 1/3, right? These were something I could apply the power rule to. This is not these. So I can't just apply the power rule or do the same thing we did with exponentials for something like this, where you have a variable base to a variable power. So again, we're going to be going through this logarithmic differentiation procedure here for functions. Most of them will look like this. Again, you can always do it. You can do it for any function, this logarithmic differentiation, but it's most useful in these cases. So back to our question. So we're asked to use, logarithmic differentiation to find a derivative. So see how this is going to have a variable base, secant of x. And remember the powers on trig functions are put after the name. So you have a variable base, the secant of x, but also a variable exponent, right? A variable power, this 2x plus 5. All right, so we're asked to find y prime, right? Find the derivative with respect to x. So like I said, I'll put the steps up as we go. So we got y equals, this is the secant of x as the base. And I know they put the power here, but remember that means you're raising the secant of x to the 2x plus 5 power. All right, so this logarithmic differentiation. First step, I'm going to take the natural logarithm, all right, log base e of both sides. So the left side is the natural log of y equals, the right side is, the natural log of this, secant of x raised to the 2x plus 5 power. Okay, then you're going to use properties of logarithms to rewrite each side. So this side over here, what's inside the logarithm is all raised to a single power, right? So I can take that power and pull it out and make it a multiplier, make it the coefficient of the log. So use properties of logarithms to rewrite both sides. Now the left side I can't really do anything with. It's just the natural log of y. But I'll say use properties of logarithms to rewrite. So left side still just natural log of y, but then I apply that power property here, this power of 2x plus 5, I pull that out front. Don't forget to put parentheses around it, right? It's that whole power is now the coefficient of the natural log of the secant. Again, the power came out. And then we're going to find y prime using implicit differentiation. So I did something similar to this earlier when I was, when I was finding the derivative of the exponential functions, right? Base e. Did something similar to this earlier. Well, this will be a little more involved. But using implicit differentiation. So remember, I'm taking both sides here and we're going to differentiate with respect to the independent variable, which is x. Remember, y is a function of x, right? Y is this thing with x's in it. So on the left side, when I do the derivative, it'll be, the derivative of the natural log of something is 1 over that thing, 1 over y, but then chain rule, right, times the derivative of the expression inside, so that's where the y prime's coming in. Equals, and then over here on this side, I have a product. All right, this is a product. When I differentiate this side, got 2x plus 5 is my first factor, and then this natural log of the secant is the second. So again, I leave the first factor the way it is, this 2x plus 5, multiplied by, and then the derivative of the natural log of secant. Now, it's not just the natural log of x, so I'm going to have to do chain rule here. This is a composite. But remember, the derivative of natural log of secant, that'd be 1 over secant, so 1 over secant x, times, so this will go in the numerator, the derivative of secant, but that was secant x times tangent x. So you see how the secants here will cancel, and I'm left with just the tangent x here, so it's 2x plus 5 times, the tangent of x in this first term, plus, and then the derivative of the first is just 2. All right, so that's just simply 2 times, and then leave the second one alone, the natural log of the secant. And then we solve for y prime, right? So y prime is all of this, right? So it's this 2x plus 5 times the tangent of x, right? That was the first term, plus, 2 times the natural log of the secant of x, right? It's that entire side, to get y prime alone, I multiply by y times y, and then we sub back, right? Y was this thing with the x's. So then the last step is to sub back, right? Y was this secant of x to the 2x plus 5 power. All right, so what I'm going to type here is, y prime equals, and in parentheses, this entire right side before I multiply by y, the 2x plus 5 times the tangent of x plus 2 times the natural log of the secant of x, all of that times, and then y here, retyping the secant of x to the 2x plus 5 power. So in parentheses, again, this quantity 2x plus 5 times the tangent of x plus 2 times the natural log of the secant of x. All right, all that times y, but y was, the secant of x raised to the 2x plus 5 power. A lot of typing there, but that's it. Now again, they put the power next to the name of the trig function usually. I just wrote it the other way. It's fine. Means the same thing. All right, so here's another one. Now this is not in that, variable base to variable power form, but I can very easily use logarithms to make this right side here a lot easier to handle. Right, it's pretty nasty right now. There's raised into powers, there's a big cube root, a fraction, right? So if I took logs of both sides, I could split this up using some properties of logs, right? So I'm still going to go through the same process, the same steps as in the last example. So we have initially y equals 7 times x to the 4th times, and then a big cube root. And then inside that cube root is a fraction, 4x minus 2, and divided by 1 minus 5x to the 4th. So again, the first thing I'm doing is the natural log of both sides. So left side's natural log of y. And then I'm going to use the properties of logs right now to rewrite this. So I got a product, it'll be natural log of each factor added up. So we got natural log of 7 plus, and then this natural log of x to the 4th, I can do the power property, pull the 4 out. 4 times the natural log of just x. And, you got times here, plus, and then this whole thing is to the 1/3 power. So I got 1/3 pulled out times, now 1/3 times the quantity All right, 1/3 with, times everything, the natural log of this fraction in here, which I'm going to rewrite as the natural log of the numerator minus the natural log of the denominator. So again, I'm just assuming you are decent at properties of logs, hopefully. Now I could also distribute this 1/3 now, but I'll leave it the way it is. So now we differentiate with respect to x. All right, so we got 1 over y times y prime again over here, chain rule. And then, 0 plus 4 over x plus, and then 1/3 times 4 over 4x plus 2, or sorry, minus 2. Because again, it would be 1, sorry, don't close the parentheses yet, don't close the parentheses yet. Because this would be 1 over 4x minus 2, but then times 4. And then minus, and then this would be, 1 over 1 minus 5x to the 4th times negative 20x cubed. So I'll make that plus 20. And then I'm taking this whole thing here, everything, times y. And that'll get rid of this, y prime equals that. And y was this thing. All right, so I got to type that afterwards, right? Type the original rule after all this. So again, a lot of stuff. So again, in parentheses, that 4 over x plus, 1/3 times, and then I had a quantity here, and then you got 4 over 4x minus 2, and then plus 20x cubed over 1 minus 5x to the 4th. This was all in the parentheses after the 1/3, and then close the big set of parentheses. So all that times y. So times y. Now y was, 7x to the 4th times, and then the big cube root there, that was in the keyboard, and then in here, all right, you got 4x minus 2 in the numerator, 1 minus 5x to the 4th in the denominator, all inside that cube root. So again, this was everything on that one side, and then again times y after. Okay, yeah, so it took a bit there. That's a lot of stuff for it to check. So this is taking a bit. Yeah, they put y first, right? I had times y after. Same thing, rearranging the factors. All right, so this is similar, all right, where I'm going to take this here and rewrite it using logarithms, and then do implicit, do this logarithmic differentiation procedure. Right, so pretty similar to the last one, just got a lot of cosines and sines and whatnot. So y equals, so the initial term, the initial expression is cosine of x, cubed. Remember, this is the cosine of x raised to the 3rd power times, and then you have sine cubed of x, and then divided by, and then down here there's 2x cubed plus 1, squared. So I'm going to do natural log. So you have the natural log of y equals, and then I'm going to apply the properties right now. And if I did the properties of logs to rewrite this, you'd have 3 times the natural log of cosine plus 3 times the natural log of sine, and then minus 2 times the natural log of 2x cubed plus 1. And applying the product rule, quotient rule, power rule for logarithms. All right, then we differentiate both sides with respect to x. Once again, this log y thing would be 1 over y, then chain rule times y prime. And then going through this would be 3 over cosine. This would be 3 over cosine times negative sine. So this would be negative 3 tangent of x. And then this would be plus, 3 over sine times cosine So this will be 3, cotangent x. And then this here, you got minus 2 over the 2x cubed plus 1, but then, times 6x squared, the derivative of the thing inside. So this is 12x squared here. And then all this is just multiplied by y. So I have a times y, where I'm replacing y with, the original expression. So I'm typing all this, where again, I'm going to call this negative 3 tangent plus 3 cotangent, and then minus 12x squared over 2x cubed plus 1. All of that in one box, one set of parentheses, and then times the original y after. I wonder if I can just copy and paste the original y. I don't know if this will work. Yo, okay, never mind. Never mind. All right, never mind. All right, so I'll type it in. Thought I could take a shortcut there. All right, so y prime equals, all right, in parentheses, negative 3 times the tangent of x, so then plus 3 times the cotangent of x. And we had minus 12 x squared over 2x cubed plus 1. Right, then all of this times y, which was this, cosine cubed of x times the sine, cubed. I'll put the cube after the name of it, name of the trig function, like typical. Then divided by, and then we had, the quantity 2x cubed plus 1, squared, and close that off. So there's everything I had on the right side there, times the original y. Great. All right, so another one where your variable base, variable exponent, right? So again, I'm going to have to use logarithmic differentiation for something like that to find the derivative. All right, so this one here, got y equals, so that 8's going to stick around, right? That's not being raised to anything, that's just a coefficient. You got 8 times and then x, base x raised to the negative 2, and then I'm going to call this x to the 1/4, right? This was the 4th root of x, so x to the 1/4 power there. So I'm going to do natural log of both sides and use the properties. Now this is a product, so I can split it up here. You got natural log of 8 plus, and then pulling the power out, you'd have this negative 2 times x to the 1/4 times the natural log of just x. All right, now when I differentiate, this left side again is 1 over y times y prime. Right side, natural log of 8, the derivative would be 0, that's a constant. And then I'm doing the product rule with these two. Right. So I leave the first the way it is, negative 2 times x to the quarter, times the derivative of natural log of x is just, 1 over x, or x to the negative 1. I'll put those together in a second. And then, take the derivative of the second term, so it'd be minus a half. So plus, negative half minus a half, x to the negative 3/4, right, 1/4 minus 1, and then times the natural log of x. Then again, all this I'm going to write, and then multiply by y, right, throw a times y over there to get y prime alone, and that's y. All right, I'm replacing y with what it originally was. And like I said, this term here, this would be negative 2, and then this is x to the 1/4 times x to the negative 1, so that's times, x to the negative 3/4 again. So I'll type that. So again, all that right side in parentheses. So I had negative 2 times x to the negative 3/4 after simplifying that first product. And then minus half times x to the negative 3/4, times the natural log of x. All right, so all that was on the side, and then times y after, right? So times this 8 times x raised to the negative 2x raised to the quarter, right? That was the 4th root of x. All right, so it's all that stuff I had on the right side, times y. All right, so something similar to earlier with a bunch of trigs here. I'm using properties of logarithms to rewrite this thing, performing logarithmic differentiation. So again, y equals, this is sine of x, squared though, sine squared times the tangent of x, also squared, then divided by, the quantity 2x squared minus 1, cubed. All right, so I'm doing natural log of both sides first, and like I've been doing, I'm just gonna, what would the properties make this look like? The product property, quotient property, power property for logarithms. So this would, after using all the properties, would be 2 times the natural log of sine plus 2 times the natural log of tangent, and then minus 3 times the natural log of 2x squared minus 1. All right, then I do my differentiation with respect to x. Again, the left side is 1 over y times y prime. And here we'd have, 2 over sine, but times cosine after, right? So this will be 2 cotangent, then plus, and then 2 over tangent, and then times the derivative of tangent, secant squared, which you could probably rewrite this in some other way, but I'll just leave it. And then minus, and then we have 3 over 2x squared minus 1, but then, times 4x in the numerator, so that's 12x up top there. So again, all that, I'm going to put in parentheses or brackets, all of this, and then to get y prime alone, times y, where I'm, substituting the original expression back in for y there. All right, so y prime equals quantity, 2, cosine over x over sine x, so cotangent x, plus, and then I'll just put this the way it was, 2 secant squared x, divided by tangent x. Nothing wrong with that. I know you could rewrite that if you wanted. Minus, and then 12x in the numerator over 2x squared minus 1. All right, so this was the entire expression on the side there, and then I multiplied by y, and y was, this thing with the original expression, sine squared of x times tangent squared divided by this, 2x squared minus 1 cubed. All right, so that's what I had on the right side, times y after for y prime. Wonderful. So again, using properties of logs to rewrite this thing, pretty similar to a question we had earlier too. A big cube root again. All right, so the original is y equals 3x cubed times, and then big cube root. And then inside that cube root is some fraction, negative 2x minus 4 in the numerator, and 3x cubed minus 6 in the denominator. So once again, take the log of both sides. And if I do the properties, we'd have the natural log of 3 plus 3 times the natural log of x, right, for that x cubed there, plus, and then I'd pull the third out, times the quantity, and then the natural log of this fraction, which I'd split up to the difference of two logs, right? Log of the numerator, negative 2x minus 4, and then minus the log of the denominator, this 3x cubed minus 6, right? All that inside the parentheses there. Now, if you want to distribute the 1/3, you can, but like I did last time, I'll just leave it. Then I do differentiation. All right, diff here, right, with respect to x. So again, the left side would be 1 over y times y prime. Right side, you got 0 plus 3 over x. So that's 3 over x plus, and then 1/3 times. And then in here, 1 over negative 2x minus 4, but then times negative 2 up top. And then minus, and 1 over 3x cubed minus 6, but then times 9x squared up top, right, chain rule. All right, so then all this, again, if you want to distribute the third, you can. put all that in parentheses and then multiply both sides by y and make the substitution back, right? This expression up here is going in place of y there. So a lot of typing. So in parentheses, right, I had on that side, I had 3 over x plus, and then 1/3 times the quantity. Yeah, -2 over, well, I guess I could just make that, +2 over +2x plus 4. And if I factor 2 out of the bottom, that'd be 1 over x minus 2, or x plus 2, sorry. So that simplifies to 1 over x plus 2. And then minus 9x squared over 3. I guess I could pull the 3 out too. Yeah, whatever. 3x cubed minus 6. Close that set, close that set. All right, so that entire thing was what I had on the right side. And then, to get y prime alone, I multiply by this y. So I'm just typing that expression for y in again. That's 3x cubed times, the cube root. There's a little thing on the keyboard here. Put the 3 there for the cube root. And then inside here, the -2x minus 4 in the numerator, 3x cubed minus 6 in the denominator, all inside that cube root. And that should be everything I had written down, times y. All right, great. All right, so I'm almost done here. And back to these expressions where you have a variable base and a variable exponent, right? So still going through this same procedure of, logarithmic differentiation, doing the same stuff each time here. So again, starting off with y equals, 2 times, and then here's your variable base, x to the power with a variable, which is -7 times the cube root of x. But instead of cube root of x, like before, I'm going to write this as x to the 1/3 power. All right, I'm doing logs, natural log of y equals, and then applying the properties of logs, this would be the natural log of 2 plus, and then using the power property here, pulling that power out front, -7 times x to the 1/3 times the natural log of just the base now, or just x. All right, now I differentiate both sides with respect to x. This natural log of y works out the same way every time, 1 over y times y prime. And then, natural log of 2 is a constant, so the derivative is 0. And then here, I'm using the product rule, right? This is a product of two factors involving x. So I leave the first one alone, -7 times x to the 1/3 times, and then, the derivative of natural log of x is x to the -1 or 1 over x, right? I'm just doing that so I can put the powers here together pretty easily. Then plus, the derivative of the first factor here would be -7/3, so I got -7/3, right? Plus -7/3 times x to the -2/3, right? It's 1/3 minus 1, -2/3. And then, leave the second factor alone times the natural log of x, right? And then I'm taking all this here, put it in parentheses, put it in brackets, and then multiplying by y to get y prime alone. And y was this thing up here, right? I'm just substituting that original expression in for y. And then x to the 1/3 times x to the -1 would be x to the -2/3. So I'm going to make this first term here -7 times x to the -2/3 just to save on typing a little bit. So in parentheses, first term in there was -7 times x to the -2/3 power. Then you had -7/3 times x to the -2/3 power times the natural log of x, right? So all of that was on the right side in parentheses, and then times the y to get y prime alone, times that y in the original y expression was 2 times x raised to the -7 times the cube root of x, which again I'm writing as x to the 1/3 power up there. And, that should be it. Right. All right, so hopefully one more. It looks like we're 3/4 of the way done. So this is pretty similar to a problem I had earlier with the secant. So it's the cosecant of x but then raised to a power that also has a variable, right? So your base has a variable, your exponent has a variable, so you're going to have to use this logarithmic differentiation to get through, finding the derivative function. So y equals, now I'm going to write it so that you see the power, right? It was the cosecant of x raised to the negative 7x minus 2 power. So natural log. So again, if I do the natural log here, I'm going to do the power property, pull the power out front, so you have the power, negative 7x minus 2 brought down, times the natural log of this, cosecant of x. Then I differentiate both sides. We're going to find y prime with implicit differentiation. Again, left side is just 1 over y times y prime. And then over here, I've got another product rule situation. All right, so I leave the first one alone, this negative 7x minus 2 times, now the derivative of the natural log of cosecant would be 1 over cosecant. Then up top, you have times the derivative of cosecant, which would be negative cosecant cotangent. And you see the cosecants would cancel. So this ends up being just negative cotangent, right? The derivative of the natural log of cosecant. So there's the first times the derivative of the second plus, and then the derivative of the second is just negative 7. Or sorry, derivative of the first is just negative 7. And then leave the second alone, times the natural log of cosecant of x. All right, so once again, all of this, I put in brackets or parentheses, that entire side here. And then to get y prime alone, I am multiplying by y, right? This 1 over y, multiply by y, get it over there. And then y was, this original expression. So I'm substituting that back in for y, and we'll get our derivative function. Okay, so y prime equals, in parentheses, right? That entire side had, the quantity. First term was the quantity, negative 7x minus 2. Then times, negative cotangent x, right, after simplifying. So there was the first term, and then the second term was plus negative 7, so minus 7 times the natural log of the cosecant of x. All right, and then close all the parentheses. That was the entire side I wrote out. And then after that, to get y prime alone, times y. And y was this, cosecant of, with the negative 7x minus 2 in the power spot of x. And this should be good. Wonderful. And that should also do it for the assignment. Great. All right, so on preview there, right? A lot of objectives, but hopefully watching me go through these here help you in some way when you're working on it on your own. And thank you very much for watching.